42 is a pretty tough problem. It's a good one. All right, I'll make it smaller here. So do you guys understand the premise is that the radius of curvature here, right? He isn't going in a full circle, but the path that he travels along here is the radius of that circle. All right, so because of that, we're able to use the relationships that we have for uniform circular motion, or for circular motion. Okay? So there's a couple of ideas we have to understand here. And first of all, we know that we're going to be able to determine his speed here because we know delta H, right? If we know delta H, we're going to be able to figure out his velocity because we know that whatever delta H is going to give us our change in potential energy, and we know that the opposite, the negative of that will be our change in kinetic energy, right? Are we gaining or losing potential energy if we're going downhill? Losing. So are we gaining or losing kinetic energy? Gaining, right? I mean, we've known since we were little kids, if you roll something down a hill, it's going to go faster, right? Or if you roll down a hill, you're going to go faster. All right, so we know that we're starting at the top of the hill. We have a radius of 36 meters. Now look, this is the part that's hard to interpret, okay? What height, so what does it mean when we say the skier just loses contact with the snow? In other words, that's one of those threshold conditions that we solve for, right? So in other words, he's sort of leaping off sort of flying off the hill, but he's just barely in contact. So we're solving for basically the idea that the normal force is going to be what? The normal force, the force that the snow exerts on his skis is going to be zero. Right, we're solving for that being zero. So that I understand this is the hardest part of this to interpret, is the conceptualizing of this problem. So right here, what we're saying is normal force at the green dot, normal force is equal to 0. But he's going in a circle. So do we know about forces required to make you go in a circle? Centripetal force. And what is centripetal force equal to? What's that? mv squared over r. All right? So based on that, we're going to be able to figure out how, about his speed. Okay, so he just loses contact. Okay, so what we're trying to find is we're trying to find h, right? I said we know h, but that's what we're trying to find actually. All right, so now we have up here is where he starts. He's going to have some energy budget that is going to be equal to his kinetic energy plus his potential energy. And then down here, he's got, you know what, I'm going to change the color of this. So we have a before and after like we did before, okay? So blue for before, green is for after, all right? And we know that the speed down here has got to be, we'll figure it out, okay? But it's going to be based on this, the stuff about the centripetal force. All right, so what's his starting speed? Starts at rest. All right, so we know we got kinetic energy plus potential energy in blue to start with, has to be equal to kinetic energy plus potential energy in green, which is when he's at the top of the circle, just barely maintaining contact or just losing contact. Doesn't matter. It's a threshold condition. All right? So now we have up at the top in blue, kinetic energy, 1/2 mv naught squared plus potential energy mgh. All right, now if we're saying that's h, then what are we saying about the dotted line? H is equal to 0 there. Good. Okay? So in other words, his potential energy at the bottom is 0. His kinetic energy at the top is 0. All right? But we'll write all that out. So his kinetic energy at the bottom, 1/2 mv squared. And potential energy is mgh final. Okay? But that's just going to be 0. Here, I didn't put this as h naught. All right, that's just going to be 0. This is 0, and he starts from rest, so this is 0. Okay? So this is that thing. If we were just calculating his speed at the bottom, what would it be equal to? You guys remember? It's not something to memorize. It's not something necessarily write down on your formula sheet for the exam. But you guys remember, it should ring a bell. His velocity, when you go down, when you start from rest, and then your potential energy at the bottom is 0, your velocity, as long as no other forces are working, is square root of 2gh. You guys remember that? We did that in kinematics as well. That comes from the eternal equation. In fact, when we did Zog and Dad's hammer and all that, that's how we figured out the idea of kinetic energy, being able to quantify it. All right, so now what we know is that H, this is what we're trying to solve for, H, all right? So we know that H is going to be equal to 1/2 mv squared over mg. I could have canceled out these m's before. So we get that it's equal to v squared over 2g. You guys recognize that from anywhere before? Anybody recognize that? Does it look familiar? Y max, when we're doing projectile motion, when you shoot something up in the air, the height it achieves is v squared, v naught squared over 2g. That's good, Austin. All right. So now going from here, but we don't know what v squared is, do we? All right, so now let's take a look at when he's at the top of the circle. This is where we're going to have to use the stuff from centripetal force. When he's at the top of the circle and he's just barely keeping contact, we know that normal force is equal to 0. So what forces are acting on him at the top of that circle? As he's going along the top of the circle. All right. What else is acting on him? Nothing. That's it. Okay? So mg is the only force acting on him. So look, net force is equal to, what do we know it has to be equal to? We did it up there already. mv squared over r. And we know that net force has to be equal, is going to be equal to mg in this case. So setting those equal to each other, mv squared over r is equal to mg. We go through, get rid of the m's, and so what is v squared equal to? gr, okay? We could take the square root and then square it again, but what we're looking for is just v squared, okay? So now we come back and we substitute, and we say h is equal to v squared, which is just gr, over 2g. So what does h got to be equal to? How about that? R over 2 is equal to R over 2. And if we take that from the beginning, the data we were given at the beginning, that's in the 36 meters, divided by 2 is equal to 18 meters. All right, so if he goes down from a height, it's a height change of 18 meters, not between the top and the bottom of the hill. Does it matter how far down this hill he goes? Does it matter if it's shaped like this or if it's shaped like this? Does it make any difference? No. As long as we're saying that energy is going to be conserved. So if we're saying energy is conserved, what are we saying about friction? It doesn't exist, okay? We're in ideal physics world, all right? So none of that matters. The path doesn't matter. Conservative force, all right? So no matter what, that's not the height difference we're talking about. We're talking about this height difference right here between where he started and the top of the hill. And that is that.